Hi. To heavily abridge Arnold Sommerfeld, thermodynamics is a funny subject. Now, the laws of thermodynamics were laws that were worked out in a laboratory through experimentation before we could come up with a theoretical framework that explained how they all fit together, how everything worked. Now, what was thought of as the first law of thermodynamics, it turns out, really was presupposing an important fact that if you're being careful, and theoretical physicists are nothing but careful when they're trying to work together bulletproof theories, we really should have started with just kind of a definition of how the game works. So you can think of the first law of thermodynamics as the sort of true most foundational law as being what we call the zeroth law of thermodynamics. And that's the law of thermal equilibrium. And the whole notion of the zeroth law, if we take any two objects, object A, object B, put them in contact and leave them in contact for a long period of time, they'll reach a state of thermal equilibrium. So if we were to then separate them, measure the temperature of A and the temperature of B, we would get the exact same reading that we would have if we measured those two objects together. Now, there are a couple of non-trivial consequences of this. One, as it relates to measuring temperature, if you think about a thermometer is an object. So the zeroth law essentially states that a thermometer can measure only its own temperature, which is why if you need to take your temperature, you put a thermometer in contact with your body and you wait until it comes into thermal equilibrium. Now, there are some types of thermometers that are capable of doing that incredibly quickly. Some take a lot longer, but any time you're trying to measure temperature, thermometry always involves waiting. The other consequence of the zeroth law of thermodynamics as it relates to engines is kind of obvious if you're trying to make a heat engine. The whole idea behind a heat engine, you take in heat from something that's at high temperature, you turn it into work. Well, the zeroth law tells us that engines need a temperature difference in order to work. If things are in thermal equilibrium, we can't have an engine. So that brings us to what we label the first law of thermodynamics. And the first law of thermodynamics is essentially a statement of conservation of energy, and as it relates to engines, particularly in the case where we're looking at confining a gas to a cylinder. So in the case of a confined ideal gas, we're saying that there is no organized kinetic energy of either linear motion or of rotational motion. There is kinetic energy in a gas, but it's randomly distributed, what we call internal or thermal energy. It's moving molecules, but they aren't going anywhere. And that thermal energy is associated with and based on the thermodynamic temperature. So we can think of the temperature of a gas, a set amount of gas inside a container, as existing as a sort of unique state. So energy is a form of state function, where it's a function of temperature and it is unique to each temperature that you have. Now, in an ideal gas, we're assuming that there aren't any forces, there aren't any chemistry, it's only just collisions between molecules and other objects. So in that framework then, there aren't any sources of potential energy that we need to deal with. So that's it. Thermal energy is the only form of energy that we're dealing with. Now, in terms of ways that energy can be transmitted, for the analysis that you typically deal with when you start learning about engines and how they work, we're only concerned about 2 of the 6 ways of transferring energy. There's work, because there are forces involved. That pressure in that gas, as the volume changes, results in work. And heat, thermal energy can be added to or removed from the gas. So, by most modern conventions, the change in internal thermal energy is equal to the heat added to the gas plus the work done on the gas. Now, in terms of other notations, some older sources, instead of using an E subinternal or an E subthermal as the energy, sometimes they use a U for the thermodynamic energy as its state function. That's becoming much less common, but it's something that you might see in some older sources. What is more common to see, and what a lot of folks that do work with thermodynamics regularly, the way they think of the first law is they often think about what the gas is doing when we're talking about work, but what someone else is doing when we talk about heat. So the older school way of thinking about the first law is the change in energy is the heat added to a gas minus the work done by the gas. Now with work, a negative work just means someone else is doing it. So if the gas is doing work, it's trying to lower the energy. If someone else is doing work on the gas, it's trying to raise the energy of the gas. So I try to be very specific about which work I'm talking about. Am I talking about the work done on or the work done by? Because it follows the rules of calculus more to think about the work done by the gas, but I'm going to try to stick with this convention. Now, in terms of engines, the typical manifestation of the first law as it relates to engines is about essentially accounting for energy. Another way we could restate this first law is that any energy that we get as heat from a hot source is going to be equal to the work done by the engine plus any leftover exhaust heat that's getting dumped into a cold source. So with engines and heat pumps and refrigerators, it's useful to think about the first law in terms of an energy diagram, where we have a hot source, a cold source, and a box representing our engine, or if we're doing the reverse, our heat pump or refrigerator. So whatever energy comes in through the hot source leaves as work and exhaust heat into the cold source, so the work plus the exhaust heat has to equal the heat coming in. Thanks for watching.